Been asked to try and get started a minute or so early. Most of the start's going to be waffle anyway, so it doesn't matter if people miss that. Start by saying thanks to the sponsors, especially JetBrains, and I'm not biased at all. No, actually, seriously, thanks to all the sponsors, because I think it's great what you're doing here in the community, making this sort of event free. And it's the sponsors that make that possible, all of them. So, glad we've got that slide up there. But here's my real first slide. So, welcome to Functional C++ for Fun and Profit. We've had a bit of a functional theme today, especially the last couple of sessions. And it's the first time I've done this talk at a conference with Haskell people around as well, and especially Bartos in the audience. I think he's going to be coming back if he's not here now. He said he would. So that's going to be interesting. Hope I don't get too many hecklers. I deliberately chose the name in this title, though, not just to follow the meme, but I really wanted to emphasize one difference between this talk and most talks on functional programming you might see, which is not to complain about them, but they can tend to sort of veer into the over-academic, which for a lot of us makes them possibly impenetrable, or at best, you know, we end up wondering how can I actually use this stuff. But everything that I'm going to talk to you about today is based on my own experience, mostly in my previous role at a bank, where I've used it in real-world code, solving real problems, and getting real value from it. So this is all, you know, proven techniques. So hopefully it's going to be fun as well, but also hopefully profitable. So that's the setting. So I'm Phil Nash. I'm developer advocate at JetBrains, as most of you probably know. So we have a number of C++ tools, C-Line, app code, and ReSharper C++. If you can catch me afterwards, I can talk to you more about that, but I'm going to get straight in to the talk. So, actually, before we do start, and I did say we wouldn't get academic, but what I'm going to do is I'm going to define what functional programming actually is. Because for most of us, we may have preconceived ideas which can sometimes be a bit misleading. So I want to home in on what I'm going to be focused on as what functional programming really is. But just take a moment to think about what you think it means. And you might be thinking of, you know, words like first-class functions, higher-order functions, referential transparency, maybe even monads, immutability. And all of those things were definitely important terms in functional programming. That they'll sort of form the tag cloud around functional programming as a concept. But they're not necessarily right in the middle of that. So to find out what that is, I'm going to quote from the obvious authority on this subject, which is the Haskell Wiki. So we've got some Haskell in right at the start. And it actually defines functional programming this way. It says that functional programming is a style of programming which models computations as the evaluation of expressions. There, yeah, that's highlighted. And a bit further down the page, it goes on and says, in functional programming, programs are executed, again, by evaluating expressions, in contrast with imperative programming, where programs are composed of statements, which change global state when executed. Functional programming typically avoids using mutable state. So also the bit that I'm drawing your attention to particularly there is this distinction between expressions and statements. And that's interesting in the context of C++, because C++ is clearly oriented around statements. And it may not be immediately obvious why that's a problem and how that really plays into this. So that's what I'm going to start off by talking about. But also notice that it ties that in with mutable state, and that functional programming typically avoids mutable state, but doesn't completely avoid it. And this is something that Bartos went to some lengths to talk about in his previous session, if you were here. Actually, we need mutability. We can't really get stuff done without it. It's not about avoiding it completely. It's about controlling and making explicit exactly where it is, and not unnecessarily wandering into it. So that's really going to be the theme of what we're going to talk about. So, what do I mean when I'm talking about expressions versus statements? Let's reframe functional programming as expression-oriented programming, and let's see where this takes us. Let's have a look at some typical everyday C++. It's definitely not functional, we'll come to that. But something you may have seen or written many times. It's reasonably clear what it's trying to do here. We're trying to give some variable, in this case it's an enum, a value that's dependent on some condition that's happened. And we're choosing to use a statement to do that, the if statement here. And just this simple example, we can start to examine the problems that arise because of that decision. So within the statement, so in both branches, the if and the else, the only thing we can do is a side effect. In this case, it's mutating the mutable variable. And that has some consequences. But we're having to do that because that's the only way we can get the value out of the statement. Actually, there is one other way we'll come on to in a moment, but in general, that's the only way we can get it out. That's why we need the side effect. But the consequence of that is now colour, our variable, has to be mutable. We can't make it const, even if after this if statement, we're not going to change it for the rest of the code. And we don't know how much code is below this, but there could be plenty. And that means that at any point in that code, when we're trying to reason about the value of colour, well, we have to consider every other line that it's possibly been through. It's sort of complicated that value with the rest of the code base. And that's just one variable. And it may not be a big scope here, but the thing is, this is the default way that we write code in C++. Mutability is the default. So much so that we don't even think about these problems. We try to pretend that they don't exist. But just because we're not immediately aware of them, just because we pretend they don't exist, doesn't mean that they don't and that we're not affected by them. And we usually end up having to debug after the fact and just consider that the cost of doing business. It doesn't have to be that way. It might be slightly harder in C++, but we can do it. Another problem with this is because we don't have the value when we declare our variable, we have to leave it uninitialized. Now, we could give it an initial value, maybe some sentinel value, but that doesn't seem very nice. Or maybe one of these values and then only set for one branch of the if statement. But none of that's really capturing our intention. And it doesn't really solve the underlying problem. So they're the problems that are arising because we're using a statement here. What if in C++ was an expression rather than a statement? So this is not real C++. This is how it might look if were an expression. So now rather than a side effect in each branch, we have a value or some other expression that evaluates to a value. And now because of that, the whole if expression evaluates to a value. And that value can then be used to initialize our variable. So we can make it const. We don't have an uninitialized value at the start. And a bonus, now we can use type inference as well. We couldn't do that before. So that seems to solve all those problems. So it's a shame that we can't do that in C++. In fact, if you look at another language, if I'd known the Haskell people here today, maybe I would have done that, but I've chosen F#. It's one of my favorite languages. It looks very, very similar. There's obviously some minor syntactical differences, but basically that's exactly what we tried to write in C++ here. Now, I do have a superpower in that I can read minds, and I know that everyone is saying, but you can do that in C++. And of course you can use the ternary operator. And actually that has all the same properties. It solves all the same problems. So what's the problem with this? Actually not that much. A lot of people don't like the ternary operator. They claim it makes things unreadable, unmaintainable. You can get problems with order of evaluation. And there's some truth in those things. You have to be careful with it. It's not very, very scalable. Certainly don't nest these things. That really does look awful. And generally, some judicious use of round brackets, the ordering problems go away. So I do use this sort of style a fair bit. It's quite a nice, neat way of doing it, idiomatic. The problem is, this just doesn't scale. It's not general enough. So if we look at another example, this time with a switch statement, so now we've got more cases. Well, this doesn't translate to a ternary operator. We've got all those same problems back. How can we deal with this one? How can we make this into an expression? Remember a little while ago I said there was one other way of getting a value out of a statement without a side effect, without an obvious side effect. And that's actually, ironically, to use another statement. In this case, the return statement. So if we push that switch block into a lambda expression, and obviously we're capturing the variable as inputs, we can now return out of it. We haven't had to mutate anything. And then we immediately invoke that lambda at the end. That's the bit that's easy to miss. In fact, some other communities, this has a name, an immediately invoked lambda expression. or an immediately invoked function expression. And starting to see that name pop up in the C++ communities as well, because this is actually a really useful way of doing it. But you might be looking at this and thinking, it's a bit of a heavyweight solution for a simple problem. You know, I had a nice simple switch statement, and I'm wrapping it in lambdas. I've got function call overhead. Well, consider this. This is actually less code than the previous slide, at least in the switch statement, because we got rid of the breaks. Sometimes it's a wash. Point is, it's not going to generate significantly more code. What about a runtime? You know, the function call overhead, returning complex values potentially. Well, you would expect any decent compiler to optimize all that away. And in fact, I checked this example with the Visual C++ compiler, and also GCC and Clang on Compiler Explorer. And essentially, they boil down to identical code to the imperative version I just showed. So there's no runtime overhead either, at least in this case. Not always the case. If that performance really does matter in these things, do measure. But again, consider this. If the value that we're returning is not just a simple integer as here, more complex type, then we may actually get more performance this way, because the compiler can reason about this code better as well. It's not just for us to reason about. The compiler has more scope for optimizing things because it knows that no one else is going to mutate this thing on the way out. So it can do things like, you know, guaranteed copy elision and return value optimization. So this may actually be better performing as well. One of the complaints sometimes you hear about functional programming techniques is the performance. And that's going to be true in some cases, but not in all. So don't let that put you off. I think this is definitely something worth exploring. I've used it to good effect. It just takes a little bit of getting used to, that's all. It's one way to turn your statements into expressions. So that was if and switch statements. What about loops? For, do, while, they're all statements as well. They're basically the same problems. You can use essentially the same solutions, but actually the problem more is writing raw loops in the first place. So if you're in the functional programming community, you're more likely to reach for the high-level constructs. And we have some of those in C++. We've got standard algorithms. I wouldn't necessarily recommend for each for this, because that's not much better than the raw for loop, and a range-based for loop will be clearer these days anyway. We want to reach for the ones that actually are closer to the problem we're trying to solve. Standard transform, standard accumulate. In fact, there's a whole set of these algorithms that do take callable objects. So these are all called higher order functions because they take or return a function or a function-like object. And that's all that term means. I have said previously that this is the complete set, and as someone pointed out, there are some others. It's not that important. What's more important is that there are some problems with these in C++. If you want to use them in a functional way, and we'll come back to that a little bit later. But the reason I've highlighted the three at the top is because they very loosely map to these very important functional algorithms: map, filter, and reduce. I know particularly that last one, it's not strictly reduce, it's a left fold, but they're similar enough for our purposes. So they're useful to know, and hopefully we'll get more general versions that will solve the problems that we'll talk about later at some point. So I'm going to move off the subject of statements for the moment, and I want to pick apart a bit more this idea of mutability, because we sort of talked about that as being a problem, and we've hinted at why, that it's easier to reason about code if you know that something can't change. And that gives us a property called local reasoning. When things are immutable, then you can look at one piece of code in isolation from the rest of the code base and have an idea of what its values are going to be. But in C++, again, we get problems when we try to use immutable types. It was simple enough in the case of an enum or an integer or a string or something, but what about when we get more complex types? So this is where I want to talk about builders. And I call this section the builder pattern, and I've heard that name used, but I don't think it's necessarily universally accepted. The important thing is not the name, it's the idea. And it is a simple idea, so I think it deserves a simple name. Let's have a look at the problem first of all. So imagine we've got some class, called it a struct here, and we want to make this immutable. So the first problem we have in C++, again, mutability is the default. So we've got to sprinkle const everywhere. And not just at the top level, Because the second problem is that const is not transitive in C++. So we've got a couple of pointers in here. The things they're pointing to also need to be made const. And then those objects, well, their classes, they also need to define immutable types. Otherwise, you're going to get problems further down. So you have to do this all by convention, unfortunately. But we can do it. You know, we're used to doing that sort of thing in C++. And it sort of feels like it's a bit more verbose. But actually, and again, doing extra things, extra verbosity is something that a lot of people complain about when they try to use functional techniques in a language like C++. But as well as what you're having to add to make this work, you also have to consider what you don't have to do. Notice I've got no methods in here. Now, I'm not saying that there's no place for methods in a functional programming view of C++. But very often, particularly for these sort of domain types, they really are just capturing, you know, a set of fields, really. It is just data. And usually we're adding methods to these things in order to encapsulate constraints on the mutability of that data. When you don't have mutability, you don't need to enforce those invariants anymore. Really, just once when you're constructing, if at all. So a lot of those things just go away. That's a lot of code you haven't had to write. Notice I haven't even got a constructor on here. In fact, I've deleted the default one because it's not usually useful to construct one of these in a default state. You need to construct it in a fully formed, fully valid state. So I like to delete it just to clarify that that's my intention. So how do you construct one of these things? You could add a constructor, but actually, because it is just a collection of values, C++ now, you can use member-wise initialization to effectively give you a constructor for free. So it does fix the order of your members, but that's usually fine. So here we're constructing one of our employee types. So we've got to pass it ready-made values in, and it looks simple enough. And if you can stick to this, that's great. This is a nice way of doing it. Unfortunately, in the real world, things get a bit more messy. There are often complex dependencies between these values, and you have to do a lot of work up front just to get them in the first place. Especially where, say, two of them here are themselves immutable types you've got to construct in a similar manner. So I've tried to sort of emulate that sort of messiness in this contrived example here. And by the way, this is sort of really distilled down from the experience I've had working previously with financial data, where we have like complex object graphs of these things we're trying to put together. But this should serve the purpose. So you can see there, you know, we're doing quite a lot of work up front to get these values in order to finally then construct our immutable type. Okay, you know, again, is that the cost of doing business? Well, maybe. Maybe we can do a little bit better. So notice that effectively we're replicating the structure of our immutable data type out here in local variables in order to progressively populate them as we get the values in. It almost seems a shame that we're throwing away this mutable type that would allow us to do that, progressively populate fields as we get their values, in order to, you know, achieve this, these immutable data types. So, you know, can we have our cake and eat it? Yes and no. We can do sort of something halfway in between, and that is to say, well, since we've replicated that structure anyway, let's just formalize that a bit more, and we'll create like a parallel companion type called a builder, which has essentially the same fields. Notice they're not const, at least not at the top level. Now we can mutate them. They may be the same types, they may be slightly different types that are easier to use when you're building it up. That depends on your problem domain. Now I've also got this build method here. That's not essential to this pattern. It's just something I found useful. It's just sort of turns the whole thing into more of a factory then. So in this case, we can also enforce, for example, that it's always created on the heap, passed around by shared pointer. That can be useful, or maybe not. That's so that part is optional. It does also give you a place to do validation, so you don't even put extra constructors in your immutable types. It keeps them simpler. So how does that then affect the usage code? So now we create our builder at the top, default constructed. We'll progressively populate that as we get values in, and then when we're ready at the end, we do .build. That gives us our immutable type. Doesn't seem like we're solving that much here. But what I want to draw your attention to is the way that we are clearly delineating lifetimes here. We've got this phase here where we're dealing with the builder type, where we're in this sort of mutable constructor phase. You know, we expect mutability. But it's only short-lived. It's only until we've got all that information, and then we transition into this nice, pure, immutable stage where we can pass this employee around knowing that we've got all those strong guarantees, knowing that we've got local reasoning. And there are other benefits as well, such as concurrency that we'll talk about a bit later that may also come into it. So we can control this, hopefully even keep it in a single block. But sometimes even that's not quite as simple. For example, looking up the address, you can see that we're having to pass it into this contacts book. And in this case, that's immediately returning it. But what if that was backed by a database? And we actually have to go away and wait for the database to come back. We might write code something like this. So I've got an explicit await method here. This could all change with coroutines, of course, but right now you see these sort of APIs where you pass the person in, and then the second argument is this lambda that's going to get called back when the database returns, and there we can continue populating our builder. Notice that I've used C++14's generalized lambda capture to move our builder in. So it should be reasonably efficient. If we had all of these variables as individual local variables, we'd have to individually move each one of those in. So that's another win for the builder, I think. We also have to make our lambda mutable. That's just C++ syntax, I'm afraid. But now, when we come back in, we can continue populating our builder. It all looks, again, relatively, well, I mean, it is imperative code. But at the end of it, we get our immutable builder, immutable build type, shall I say. So it's difficult to convey just in a couple of slides why this builder pattern is useful. Maybe I haven't convinced you in this sort of domain type example. So I use this extensively, and it really solved a lot of problems in a large, complex system. But the ideas behind it, particularly this separating this mutable phase from the built phase, is really sort of a foundational concept. And I'm going to pull at that thread a little bit more. And rather than talking about a complex type, I'm going to go back to a simple value type, but one which in C++ is still a little complex. And I call this section a fast and safe ref-counted string. And you might be wondering what ref-counted strings have to do with functional C++. If you've been around C++ for a while, you may remember that the original design of standard string was such that it was meant to be at least possible to write a reference-counted implementation. And most, if not all, early implementations were. But there was a couple of problems with that. The first relates to the fast. In fact, before we do that, let's just recap how this is actually implemented. So the real problem is mixing reference counts with mutability. And we solved that with this technique called copy on write, or CAL for short. And I'm sure you're all familiar with how that works. But I'm just going to recap it anyway, because we're going to build on this a bit. So we've got a single buffer up there with some characters in it. And we've got 3 strings pointing at that buffer, and then the reference count. So the reference count is 3. So they're sharing the underlying data. That's good. It makes it nice and cheap to copy and pass around. The problem comes when we need to mutate one of those strings, because standard string has a mutable interface. So we mutate in that 3rd string there. So at that point, we take the copy. So at the point of write, hence copy on write. So the ref count for the original buffer drops to 2. A new one has a ref count of 1. But that seems to work. That seems to have solved the problem. But the 2 problems I wanted to talk about. The first one is that turns out cow runs like a dog. And the reason for that, well, 2 reasons. First of all, those ref counts have to be atomic, because when you have multiple threads at play, those threads can be consulting the reference count, so they need to be atomic, either by protecting them with a mutex, which a lot of early implementations did, or at least using atomic intrinsics, which, again, 10, 15 years ago, they weren't as good as they are now on modern hardware. So that was a problem. Second problem was that it's very easy to accidentally call a mutable function or method on string when you didn't actually need it. And we found some ways to make that less so, but still, we were hitting that ref count more often than we needed to. So that was the speed problem. But perhaps the bigger problem is that it was also unsafe. There are situations you can get into where you have iterators or pointers into a string, and then a mutation on another string can invalidate them. And that was actually allowed by the first version of the standard in order to allow reference counted strings. But that was fixed in C++11. C++11, it's no longer possible to write a standards conforming reference counting string with copy on write that actually has any value at all. So that was the main reason that GCC, I think, was one of the last holdouts. They changed their implementation. So now pretty much all strings use the small string optimization, where it has an internal buffer. And that's fine for the general case, but it's a shame we've had to give up this ability to freely share large strings in a reference counted implementation. We'll rewind a bit. We actually said that the whole problem only came in when we introduced mutability. So what if we started with an immutable design? Go back to that first example again. Got our buffer, ref counted, got 3 strings pointing into it, sharing the same underlying data. That's it. It's the end of the story. We haven't got the mutable part to worry about. So none of those problems really come into it. Well, we still have the ref count, but we don't consult it nearly as much. And we certainly don't have that safety issue. So what is the problem with this? Well, the one limitation is that there is a reason that standard string has a mutable interface, and that's that we do actually sometimes want to mutate strings. So how can we have our cake and eat it again? How can we have it both ways? Well, this is where the builder pattern comes back. So actually, before we get to that, there's one other thing which may mitigate it sometimes, and that is now that in C++17 we have string views, so pointers into an existing string or sequence of characters can often play the role of mutable strings, particularly when you're taking slices like a substring. But the real solution is to have a string builder companion type. So this is now optimized for mutability. That's its purpose. So yeah, you can mutate things in place. You can truncate strings. You can reallocate them and make them bigger. You can reserve them. You can write into an underlying buffer. Whatever you need to do to get the job done, because now we're controlling it to that small scope where that's necessary. And you're restricting it to there. Notice it does also have a reference count. It's not essential, but there's a benefit to doing that, even though string builder will never actually touch that reference count. Because once you have got it into the shape that you wanted, then because you no longer need the builder usually, you can move or detach, depending on how you want to call it, the underlying buffer into an immutable string. Now you're transitioning from that builder phase into the immutable phase. So the string builder can no longer change it, so it's safe. The immutable string obviously is not changing it, so you can freely share it. And just as before, we can take copies that only impact the reference count. So that reference count itself also just moves in. It hasn't had to be touched, so no atomics need to be invoked. And then later, after we've been passing this immutable string around for a while, maybe, and this actually doesn't happen very often, at least in my experience, maybe we still want to mutate it. What can we do then? Well, we could copy that back into a new string builder and mutate that. And if that, well, in this case, that's shared, so we'll have to do a copy. But if it was the last immutable string holding a reference and we didn't need that anymore either, we could even move that back into the string builder. So we haven't given up any of the performance advantages of copy and write, but now we've made it safe and efficient and explicit. So that's actually really nice. There seems to be like no downside at all. It's all upside. So it's a shame we don't have this in the standard, at least not at the moment. I'm not sure if there are any proposals for anything like this, but I know that there have been rumblings about redesigning string, but it's a big job. But just to be clear about what we're talking about, it's all about controlling the scope and lifetime of our sort of mutable construction phases from what would hopefully be most of your program, where you're just using the immutable values that are produced by it. So this is a really nice way of keeping that separation. So that's strings. Now strings are, in a way, just a special type of array. So you might think, well, can we do the same thing with arrays? And yes, technically you can, and I did. My previous role, I had array builders, immutable arrays, array views, all of those things, and they were useful, but not as much, because we tend to use arrays in different ways. They're often much bigger, so when you do have to copy, that's more expensive. We tend to mutate them in place more. There's a lot of problems. So quite often we ended up falling back to standard vector anyway. So arrays are not a great type to talk about here, although if you're prepared to go non-contiguous, there are some techniques to help with that, but I'm not going to go into that one today. But I do want to talk about different type of data structure, more of a tree type of structure. And the technique I want to talk about here is called persistent data structures. So it's another thing we've borrowed from the functional programming community. And I want to be clear about this word persistent here, because often when I tell that to someone for the first time, they think I'm talking about writing to a file or a database or something like that. It's nothing to do with that at all. What persistence means here is that when you do what you might think of as a mutable operation, like adding a new element, you're actually getting back a new version of the whole collection, and the old version still persists, still hangs around. That's where the word persistence comes into it. So let's just illustrate this with the simplest example of a singly linked list. So I'm sure you all know how singly linked list works, but I'm again going to recap very quickly to make sure we're all on the same page. So each node in the list holds a value and a pointer to the previous or next, depending which way you look at it, item in the list. Simple. Has to be a singly linked list for this to work. You'll see why in a second, because if we add a new item at the head of the list, then obviously we've got a pointer back to the previous head and the new value, but crucially, the original list knows nothing about this new item, and the original list can quite readily persist, continue, as well as the new list. So usually we'd have some sort of wrapper object, the list itself, that would hold the pointer to the head, and usually a size as well. So these two things can persist. And notice in this particular case, there's pretty much no overhead in having these two in memory at once. That's really quite interesting. And we can do this the other way as well. We can remove items from the head, and we can stack these things up in lots of different ways, very efficiently keeping all the common state shared. So it can be really efficient, but obviously if you have to do mutable operations further down the list, then it involves more copying. It becomes less efficient. Well, the big problem with lists in C++, of course, is all the pointer hopping, the cache invalidations. They're not particularly performant. We don't tend to use them very much. But that was lists. I didn't really want to talk about lists, other than that when you finish with all your additional versions, you can drop them. What I wanted to talk about is more of a tree type of structure. This is just a simple binary tree. So we've got a number of values in here. If we want to introduce a new value, or I should say, again, I'm sure you know how these work, but it does require a strict weak ordering of the values. So at each point in the tree, we have 2 pointers, and which pointer we follow depends on whether the value is less than or greater than the parent. So if we've got a new value that comes in and we want to insert it into this tree, we're going to navigate down the tree, going left or right, until we find the slot that it should go into. There's usually 2 places it could go into. The simplest one is to add it to an existing leaf. So we'll put it in there. And to add that to the tree, we need to write into the pointer of its parent. And if it's just a normal mutable tree, then we're done, nice and simple. But if we want to make this immutable and persistent, obviously we can't do that. We'll have to rewrite or copy that node, mutate into the copy, and then we've got another new node, and we need to write into its parent. So we're going to end up invalidating all of the nodes up to the root. But having done that, we now have 2 roots, the new root and the old root. And so the whole of that original tree is persisting. That's still around. And then we have a new tree. It's got 1 new branch, and then all of the common state is shared. Or all of the common state we didn't have to copy. So there is a little bit more of a copying overhead, but because of the width of the tree, it's a lot more efficient in sharing than the list gets when you have additional copies. So that's quite nice. So that's how you make that persistent. The problem with this being a simple binary tree is that you can get very unbalanced trees, especially if you load it up with already sorted data. So we don't tend to use those. We use different strategies for balancing the trees. And I'm not going to go into this too much, but we usually use red-black trees in C++. And here's the rules for red-black trees. So it's not that important which one, but I'm just going to run through how that tree would look if we apply those rules. So we colour each node red or black. It's just sort of an arbitrary distinction, usually with no overhead if you implement it right. So if we add our new node down here, well, this violates one of the rules that says that red nodes only have black children. So what we do is, at each stage, we consider the immediate parent, grandparent, and uncle nodes. And in this case, what we have to do is just recolor them. Basically, just switch those colors around. Sometimes we may have to shuffle the nodes as well. So now we've restored that invariant here. But the next level up, we've now got 2 red nodes again. So we just recursively apply that up until we get to the root. Now we've got a root node invalidation, because that needs to be black, but that's easy to solve. We just change it to black. So that's how that works. Let's say that the specifics of the rule is not important. What's important is that now, having done that, we've had to touch all of these nodes, which, if we're making it persistent, means we've got to copy all of these nodes. There's some additional overhead involved. We can do that. This is all quite possible. In fact, if you look at Wikipedia under red-black trees, there's a section in there that says that red-black trees are also particularly valuable in functional programming, where they're one of the most common persistent data structures used to construct associated arrays and sets, which can retain previous versions after mutation. So just what we were talking about. So it's commonly used. And in fact, an implementation that I wrote a couple of years ago now, we sort of mitigated some of that copying overhead by, ironically, using a form of copy on write. Whereas you're navigating down, you keep track of the shared state. So if you're mutating something that's not shared, which means it's not visible outside of the red-black tree, you can mutate it in place. And that's safe because we're effectively in that construction phase. So thinking back to the builder pattern again, separating those lifetimes is what makes this possible. But then if you take a copy later, then you have to copy the shared nodes as well. So we can do that with red-black trees, but unfortunately red-black trees themselves have fallen out of favour in C++ circles these days. You know, we're all about the hash sets now. They're much more performant, have better complexity guarantees. Unfortunately, hash maps, as we had them in the standard at least, not really possible as far as I know to really make persistent in a useful way. But what was the problem with the red-black trees in the first place? Well, the problem is that they get quite deep. So let's say you loaded a red-black tree up with about 15 million entries. Then you're going to have a tree depth of about 24 nodes. So that's 24 pointer hops to find any individual value on average, which is quite a lot of cache misses. And the reason they get so deep is because they've only got 2 pointers per node. So if that's the problem, the solution is obviously just to add more pointers. And in short, that is the solution. But that raises a couple more questions. So let's see how we can answer the questions. And the first one, perhaps the most obvious one, is how do we know which pointer to follow as we're going down? So in the binary tree case, we only have to just do a comparison, less than, greater than, left and right. But if we've got n number of pointers, how do we know which one to follow? So we'll have some sort of array of pointers like this. As we'll see in a moment, not all of them are actually populated necessarily. But to know which index into the array to use, what we do is we hash the value, and we'll start off by taking the first few bits. In this example, I'm taking 5 bits at a time. That gives you a value, so 27 in this case. That is your index into the array. So if there is a value there, we can now follow that down. Maybe that is another branch. And if so, we'll look at the next 5 bits, or however many we're taking. That gives you a new value. So 6 in this case, that's the new index. So in this case, that's giving us a leaf, but maybe this will go down 4 or 5 levels before we get there. So this is called a hash tree, or hash trie, depending on how you pronounce it. Similar to tries that you may be familiar with for string dictionaries, where you take each character as the index. But here we're taking parts of a hash value. So it's it's a much more general approach. I said there were two problems. And the second one stems from the observation that, well, particularly in this case, most of those slots for pointers in the array are empty. This would be very wasteful, holding, in this case, 32 pointer size items and not using most of them. So that sounds like the ideal case for some sort of sparse matrix, sparse array. So that's sort of how we do it. So we have a single integer, which is a bitmap, where each set bit represents a set item in your logical array. And so the unset bits are the empty items. And then you have a compactor representation of the array of pointers. So in this case, we only need 3 items. So 3 items and a single integer is all we need. How you do the mapping is quite an interesting problem in itself. There's very efficient solutions. By the way, I've done a whole talk, 90-minute talk, on just this data structure at CPP Now just recently, which is available in video. So I'll go into that in much more depth there, including the implementation. If you're interested, go and watch that. There will be a link at the end. But just be aware that there's some extra trickiness there. What that gives us then is a tree more like this. So notice many of these have more than 2 pointers, and they can be up to 32 or 64. And our path down the tree is by peeling off sets of bits from the hash. And that's pretty much it. But what this gives us then are, for example, with a 32-bit fan out, we've got a maximum depth of 6 or 7, depending on whether you take the last 2 bits, levels deep. And in fact, for that example I mentioned earlier, with 50 million items in it, you're going to get an average depth of 5, which is significantly better than the 24 that we saw with the red-black tree. So that's the main reason this is better. Because it's hash-based, the leaves actually hold arrays of values, so we need a strategy for handling them, whether it's a linear search or a binary search. There are options there. This turns out to be more space efficient than hash tables because of that sparse array optimization that we used. Complexity is log 32, which is not so meaningful to most people. In practice, and this is something I talked about in my CPP Now talk, the performance characteristics much more closely resemble hash maps than the red-black trees. And the really nice aspect is, assuming you have a good hash distribution, there's no rebalancing involved. The hash distribution itself is your balancing of the tree. So because there's no rebalancing step and the trees are much shallower, these are much nicer with respect to persistence, because there's much less copying involved. So this is almost ideal from our perspective of a persistent data structure, which is why I did a talk on it at CPP Now. So that's how we can use immutable data types even in complex ways. There's obviously a lot more to it than that. And by the way, these persistent data structures are sort of really key pieces of the puzzle if we do want to get a software transactional memory at some point, as Bartosz alluded to earlier. Okay, last section, again, slightly different direction. I'm going to talk about another data structure. And in a way, if you were in Bartosz's talk just before this one, he spoilt this a bit. I like to build up to a bit of a surprise, but this data structure is probably the simplest one that we have in the standard as of C++17. So of course I'm talking about standard optional. Bartosz implemented his own version of this in his talk, partly because we don't strictly have this in the standard yet, and partly because this doesn't have everything we need. But we can build that. So let's just review what it does. It represents something that either has the value you intended or nothing at all. And it saves us from having to use sentinel values or sort of mix it with pointer semantics when we didn't actually need to. But in practice, the way it's implemented in the C++ standard, it does look like using a pointer. So you can track it for truthiness like you can with a pointer. You dereference it with the asterisk operator. And there's a certain level of unsafety about this. You can dereference it without checking it first. The option types or optional types in functional programming languages usually have solutions for this. So it's a shame that we don't have that, but we do have some features. So we have the value OR method. So with value OR, we can provide a default value that it's going to fall back to if we don't have a value in the optional itself. And that's good. That's a common use case. That makes it safer to use, nice and expressive. But it's not very general. In particular, I mean, here it's just a constant integer, not a problem. But maybe it's a more complex object, or it's something we have to go away and compute. We don't want to do that work if we actually had the value in the optional after all. So we want to somehow make that a bit lazier. And we could do that easily enough with a helper function. So I'll call this value or again. You pass the optional in, and a lambda. Bartos shows something very similar to this. So we say if we have the value, we'll just dereference and return that. If not, we'll defer on to our lambda and return that instead. And now we can write something. I haven't really taken advantage of it here. I'm still returning a constant, but we can do anything we want now in that lambda. So that's nice. But now we've done that, maybe we can go a bit further. Maybe we can do it the other way around. So here, we're doing something if we didn't have a value, but we can also do something only if we do have a value. So I've called this with. It's not the best name. We'll look at a better name in a second. But yeah, we're just doing exactly what I said, only doing something if we do have a value. So now we can write something that will get the dereferenced type. So it's safer to use because we're not having to dereference it ourselves here. But notice what we've done with this. Think back to where we started. What we've done is we've given this statement semantics. We're having to rely on a side effect in here to do anything. That's a shame. But we can fix that. What we need to do, really, is make our function have an else statement and return a value. So the lambda has to return a value too. So now, in our lambda, we just do a computation and return something. So what we get back out here is still an optional. In this case, it's an optional of the same type. So we're getting somewhere, baby steps. But it's a shame that we had to have an optional of the same type. Maybe we can fix that as well. So there's a bit of boilerplate at the top. Don't worry about it too much. It's really just some simple traits for making sure we either have an optional, well, we always have an optional even if we returned a non-optional. And then we use decal type on the result of the lambda to work out what we need. Other than that, it's basically the same. And now we can return something of a different type. So in this case, I'm doing a string conversion. So that's quite nice. Now we've got this. Note that we're taking an optional and we're returning an optional. So we can actually pass the result of one of these calls to another. We do something like this. So now we've got an inner lambda, returning an optional, passing the result of that to this outer lambda, doing different things. So we're composing them together. So Bartos went to some pains to explain that's a really nice property. What's not so nice is how this reads. This is really not very readable at all. And I really struggled to find any decent way to format this to make it any better. That's a big problem with C++ again. Functional programming language has better ways to represent functional composition that allow you to create a pipeline of these values flowing through functions. So we don't have that in the general case in C++, but we can do it in a special case. And this is where Bartos really started to steal my thunder, but if we just change our with to operator pipe, that's the only change I make here. Look at what it does to the code. Now, normally when I show this slide, everyone gasps and says, that's so much cleaner. But Bartos has already ruined it and said that it's ugly. But there you go. I think this is at least much better, much easier to reason about than the previous version. And it does scale quite nicely. So we can add multiple lambdas that we string together. Obviously, we can break these out into variables if we want or not. Notice we've got an extra thing in here. This one's acting as a filter, the second one. So if the previous one returned an optional that had a value, and it passes this condition, then we return another value. Otherwise, we return an empty optional. We've got a string conversion in there as well. We could do lots of things. In fact, this is now a really nice, general, universal idiom or pattern. In fact, it's so general that actually there's very little about this. It's only really that filtering that says anything about optional at all. And you could apply these same bits of code to, say, a vector of integers or a future of integers or anything that can represent something that holds another value or represents another value in some way. So this is, with a little bit of hand waving and brushing things under the carpet, another example of a monad, the maybe monad, we tend to call it from Haskell. The fmap is basically handled by the boilerplate at the top, by the way, if you're interested. So this is really nice, but it's not something we're used to seeing in C++ very much. But if you've seen Eric Niebler's ranges talk at itCppCon a couple of years ago, he showed this example. Now, not all of this is strictly monadic, but it's using the same principles that we just looked into of composing bits of functionality using ranges. This, by the way, what he's actually doing is he's writing a calendar to stand it out. And all this formatting is happening in the code that is composing together in here. So each bit of this is doing a bit of work and then passing the results on to the next level. And to give you an idea of just how nicely this composes, that chunk 3 there, what that's relating to is the width, the number of months across. If we change it to a 2, we'd have 2 columns instead. So how nicely it's all factored out. Not always as clean, I agree, but very often problems can be broken down in this way. It's why it's such an important concept in functional programming. We just don't really have the ability to string these things together so easily in C++ yet. That's why I think ranges are really going to make a big difference to the standard. So that's really nice. By the way, that video is online. If you haven't seen it, you should go away and watch that. So I think it's probably a good point to reflect on what Kevlin Henney has to say about monads. I haven't checked with him whether this is still the case, but probably is. So let's wrap up. We started off by talking about expression-oriented programming, why that was really sort of the essence of functional programming, and how we could sort of effectively achieve that in C++. Why that employs the local reasoning, the importance of immutability in that, which really sort of threaded through the rest of the talk. Builder types to help us to work with immutable data, and persistent data structures, sort of the container side to that question. And then finally, we did talk a little bit about monads. So that's all I've got to talk about. So thanks everyone for listening. All the references, including some links to Bartos's blog actually, are on my website. This fcppref.html has a whole set of references there, so just one link for you to remember. If you can't remember levelofindirection.com, by the way, I've also got extralevelofindirection.com, and that just redirects there. Might be easier. But yeah, that's it. Thanks for listening. And if I got it right, we've got time for questions, haven't we? Any questions? Right at the back. I knew it'd be you.
I had a couple of observations here. Just a couple.
Just a couple, that's
just
not
a couple.
bad.
So when you were talking about the red-black trees,
Yes.
one is you were pointing out that you had to do a lot of recoloring of your red-black trees.
Yeah.
You can actually reduce that quite a bit. One is that in Haskell, we don't actually use red-black trees as our sort of functional map of choice. We use what are called trees of bounded balance. Dan Lyon and some other folks implemented the implementation that we have today, and it's based on some nice papers that you can find links to from the original thing. So, you might want to try that if you ever care about playing with the red-black tree stuff ever again. The other thing is that, like, Chris Okazaki wrote a paper showing like how to do red-black tree recoloring if you want to keep the red-black tree form with a little bit less path copying. So there's smarter ways to do that.
Right.
Is what I wanted to point on that one.
Okay.
And the other one was the sort of magic boilerplate you kept glossing over at the top of your slides there.
Yes.
Was I correct in reading that you're using pipe to do both sort of map and bind to borrow?
That's right, yeah.
So this leads to other problems.
Okay.
And this is actually a big problem that I have with the current standard future, the experimental future then, is that you can't build a future, right?
Right.
And this means that you can't have a maybe, which has a distinction between nothing and just nothing, which sort of makes maybe, the benefit of maybe over null is that you can actually talk about that distinction. And if pipe can only ever collapse, you can't ever build a maybe. And it's an important concept to have. So I just wanted to point out that from a functional programming concern, that raises the hair on the back of my neck as a functional programmer quite a bit.
So this is the 8th time I've done this talk, and I've been waiting for someone to call me out on that, so thank you.
So those are the concerns that I had to raise, sorry.
Any other questions? Okay, well, I'll be around, so if you've got any more questions, come up and see me afterwards. Thank you.